Hello everyone. Today is the 54th day of Leetcode 75 challenge. Let's begin with the 54th question. Question 2300. Successful pair of spells and potions. I will request you to read the question beforehand as I will deep dive into the PPT and explain it in simpler way. Now, let's understand the problem in the easiest way possible. So, you are given two integers arrays, spells of length n and potion of length n. Okay? Each element in spell represents the strength of a spell. Each element in potion represents the strength of a potion. So basically, you have a list of spell of size n, and each value here represents the strength of the spell. Similarly, for the potion, you have a list of size n, and each value here represents the strength of the potion. Okay, you are also given an integer success, a spell, and a potion pair is successful if the product of their strength is greater than or equal to the success. Okay, so you have been given a success variable and it has a value, suppose 6. Okay, so the product of the spell and the potion has to be greater than or equal to the success value. That means that if I take 2 from here and I have to multiply 2 with 3 also, 2 with 4 also, and 2 with 6 also. Okay, so here we could see that 2 into 3 6, and 2 into 4 8, 2 into 6 12. All of these three pairs, or basically the product of this spell and potion, all the threes are greater than 6, right? Therefore, for this particular spell, 2 with the strength 2, the answer would be 3. Similarly, we will take spell value 3 with the strength of 3, and we will multiply this 3 with all of these numbers in the portion, and we will check that if product is greater than the value of success. Our task is to return an array pairs of length n, where pairs of I is the number of portions that can form a successful pair with the ith spell. Okay. Now let's understand the constraints. N equals to spell's length, m equals to potion's length, and n comma m. Both of their values could be from 1 to 10 to the power 5. And spells of I and potions of I value also could be from 1 to 10 to the power 5. Okay. And success also from 1 to 10 to the power 10. These are the constraints, and this is the problem explanation. I hope you understood the problem explanation. So let's move to the next slide. Now let's understand the input-output explanation. So here you could see we have been given a spells list of size 3. Potion's length is also 3. Okay, they can vary. It is not important that they both of their length would be same. And success value is 16. Talk about it. Okay. So from this spell 3, 1, 2, right? And this is the potion. So what if I take 3, okay? The strength 3, I will multiply it by 8, 3 into 5, and then 3 into 8. These are the potion values, right? 8, 3, 8 into 3 gives me what? 24. 3 into 5 gives me 50, right? 8 into 3 gives me 24. So from here, we could see that 24 is greater than 6. This is also greater than 6, but this is less than, so not 6, sorry, 16. Okay. So the output for this combination would be 2. As you can see, we have 2 here, correct? Now, with 1. Now, if you take 1, 1 into 8, 1 into 5, 1 into 8. So everything is less than 6, right? 16. So there are no product pair. Therefore, output for this will be 0, right? 0 pairs. Then again, we have 2 here. Now for 2 into 8, 2 into 5, 2 into 8 gives me 16, gives me 10, gives me 16. So 16 is greater than or equals to the 16. It is less than 16. It is greater than or equals to 16, right? So therefore, the output for this will be 2, right? There are 2 pairs which are successfully greater than or equals to 16, right? Therefore, we can see the output of our, it matches with the input output. So this is the input output explanation. So I hope you understood it. Let's move to the next slide.
Before going to the further slides, let's understand what is binary search or the concept of binary search. Fine. A binary search is an efficient algorithm that finds a target element or optimal value by repeatedly halving the search space While commonly used on sorted arrays, it also applies to monotonic functions. Monotonic functions basically means, I will explain that. Okay, let me explain what is binary search. Binary search is basically, if this is a range, right? This is a range. So you keep on doing half of it. Suppose you started here, okay, in the middle, and then you will make the range half. Okay, then you have this particular range with you, then you again started in the middle, then you again make the range half, right? So this way the binary search goes. Okay, I will explain in more depth. So you could see here, it comes in monotonic functions, biotonic function sequences, and decision based problems with a clear true false boundary. So monotonic functions means increasing or decreasing, which basically means you have a sorted array in clearly increasing or strictly increasing manner, fine. Or decreasing means that the number is strictly decreasing, 5 4 3 2 1, whatever, right? So that is a monotonic function. uh, that is a range in which you will use the binary search in a monotonic function. Okay, then comes the biotonic sequences. Biotonic sequences are basically the first it goes on increasing manner, then it goes on decreasing manner, and then it goes on increasing manner, right? Or it goes in vice versa way. It comes in decreasing, then it goes in increasing, this way. These are the sequences I have given you. Okay, and decision based problems with clear true false boundaries basically just it's way like you have a range and you got a value. Is it equals to the number which we are going to find or not? Then in that case we use this decision based problem. This is just a format of the sequence which you get, in which you can clearly figure out whether you have to use binary search or not. Okay, so it works wherever the solution space has a predictable pattern, enabling us to eliminate half of its at each step. Okay, it has to be a predictable pattern, right? Since monotonic stack is a predictable pattern, biotonic is a predictable pattern, right? So though it that's the way it goes. Okay, now how binary search works, fine, that's the important thing. Suppose let's take a range. Okay, uh, 1 2 3 4 5 6. Okay, and start with the entire sorted array. So this is a sorted array, right? Now how it work? We calculate the midpoint. How to calculate the midpoint? 0 1 2 3 4 5, right? So what is the low value here? So we have two variables in binary search, one is low and one is high. Okay, and another is mid. Now low takes the uh, index value from the starting, and high takes the index value from the backside, and mid is the calculated value for the particular range mid index. Okay, so low is basically here 0 and high is right now is 5, right? And if we calculate this, how much it going to be? 5 divided by 2, you get 2, right? Okay, you get 2. So this is the mid value right now. Okay, so what happens? You got 2, right? So you come to index 2 here. What is the value of 2? It's 3. Fine, wait. Now the thing is, we compare the mid with the target. Suppose basically we use binary search to find a target value. Okay, so the target value, suppose here is 4. Okay, but you are standing at 3, right? Because you got the mid value as 2. If you could see, if it is equal to the target found, the target is less than the array of mid. Array of mid since mid is the index value, right? And here array of mid, which is array of 0 to array of 2, is the value is 3, correct? And but we were searching for 4 value. The target was to be 4. Okay, now you could see that, okay, the target value is greater than the mid value. Okay, so what you will do, you will search the right half. Now you will understand what is the repetitively halving the range. Now what will happen, your low, so low value will come here. Okay, since high was standing here itself, because this is not the range you need, right? 3 is not required in your search space, because 3, because the value which we are finding is greater than this particular value, right? So we'll make the range here, right? So what will happen now, low value is what? Low value is 3, high value is 5 right now, and mid value is 2, right? So now what happens, now you will calculate this mid value again, right? 3 plus 5 gives us what? 8, right? 8 divided by 2 gives us 4. So the mid value for this range is this, right? You come here, 5. Now you will check that, okay, this 5 is greater than the mid value, the target value, right? This array of mid is greater than this target value. Now what we'll do, we will go for the search the left half of the range, whatever you have, right? So what happens in that case, since low was standing here and mid was here and high was in the end, right? because this space is done, right? We don't require this space anymore, and anything beyond this space is not required also, right? So what will happen now? L value is 3, right? So 3 plus 4 gives me what? Divided by 2 gives me 7 by 2 gives me 3, right? We get 3. So what will happen? The high will come here and it will stand here, okay? And mid value is 3, correct? Now what happens? You check, okay, you will see that, okay, the mid value is 4 and the target value is also 4. Therefore, we found the target. So we then return this particular index, or we return true or false as per the question, right? So we repeat until the target is found or search interval is empty. If the search space says that, you might not have the target, right? And if uh, H comes here and L comes here, because basically they cross each other, that means that the value is not present in the search space. Okay, so I hope you understood that how binary search works. Now, binary search basically works on sorted array, ascending or descending, or biatonic arrays, as I said, or monotonic functions, right? So these are the ways where binary search happens. You have to look for a pattern there, okay? And why it's efficient? It's efficient because the best case is O of 1 if the middle element is the target, and average worst case is log n. Each step halves the search space. So whenever you do a half of any search space, suppose this is the search space, right? And if you iterate, it will take O of n time complexity. But if you make it a half, you came here and you make it a half, and again you make it a half. So this is a time. This is basically a mathematical calculation. When we do something, and any step, if we make the particular thing in half, 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 like a merge sort, time complexity comes out to be log n, right? So that is why it is much more efficient than any other iteration. And search complexity usually takes O one time complexity, and if you are doing a binary search space, then it takes log n recursion step. That's all. Now this binary search is basically efficient for fast lookup in sorted data, optimizing problems with monotonic pattern, reducing the brute force time from O of n to log n. Okay. Now, where binary search is used. Binary search is basically used in sorted arrays, basic direct applications like binary search question number. This I've just given you the references of the questions also, and where it is used. Right there, this is what this particular PPT is. This slide is all about. So, like first and last occurrence, if you have to find the first and last index of target, right? They find the first and last position of element in the sorted array. These are the questions where you need it. You could go and practice these questions if you want, like search insert positions. If target not found, return the positions where it would be inserted. Example, search insert position. Basically you have to insert 7, right? And you got a value 5, you got a value 6, and then 8, right? So 7 will be inserted here, right? So this could be done using binary search. Finding pink element in an array. Peak element comes in the biatonic sequence, as I explained earlier, increasing and decreasing, right? So this is will be a peak element, right? Then you have to find the condition why it is a peak element, because the left hand values are lesser and the right hand values are greater than this particular element. Now rotated arrays are also there. Rotated arrays also work as a biatonic sequence. Suppose you had 4 here, 1, 2, 3, right? So it was a rotated array this way. Modified binary search to handle rotated version. This is question number, you could go and check in Leetcode 33. Cocoa eating bananas or minimum eating speed. This is the most common and most important question to understand binary search on answer or binary search on answer space, not the array. Answer space is basically you have to figure out by yourself that what could be the range of binary search rather than depending upon the array. Okay, like you have to assume that the search space will be n, or it would be 6, or whatever, depending upon the answer. Fine. So I hope you understood the binary search concepts. Let's move to the next slide.
To understand what problem is asking, we should build up an intuition to the problem. So let's start by understanding the goal first. Okay. So we are given two arrays, spells and persons, representing strength of the spell and person respectively. We are also given the number success. We need to find how many persons can form a successful pair with each spell. Okay, that we have understood in the introductory explanation already. A pair is successful if the spell of I multiplied by the spell of j is greater than success. Right? This is clear to us. Now, for this problem, what could be the brute force? A brute force approach would be to check in all n cross n pairs, which will result in n cross n time, which is too slow for the large inputs. What it means is basically for I for spells, Okay, first loop for spells. Then here in val we could do what? We could store spell of I. Again, one for loop for the portion, and we will multiply this spell will with a portion of I, and if it is greater than or equals to the success, we will count it. Okay, and after counting, we will store it into the list. Okay, in an empty list. So, but because of this, it will take n cross n time complexity, and this is not what is desired by the interviewer or the problem. So, we aim to find a more efficient method to reduce unnecessary comparisons. Okay, so let's visualize the process. So, first and foremost thing, we have to store the count of the pairs, right? For that, we need an empty array or list. This is it. Now, if we have observed the, in the spell, this is a spell array. Suppose if it is 2, 3, 6, okay, and let this be the output array where we will store the count. Suppose it is 104. Okay, so this count has to be matched with this spell. What it means that how many pairs or how many product with the pairs of persons were there. Okay, so if you could see, if the spell value or the strength of the value is 3, there are this number of pairs. If the strength of the spell value is 6, the number of pairs or the number of values which are greater than the success is this, right? 4. So this cannot be changed, right? The sequence has to be maintained. But it is not, we don't have to put the values, right? That how many pairs or what numbers of the portions, like if portions are 2, 3, 4, or 6, right? So how, if I take, for example, 3 from the spell, and I multiply 3 with each of the numbers. So they are not asking that what were the pairs, right? They are just asking us what was the count. So the sequence or the order of how we multiply the spell value with the portion values does not matter. From there, we can figure out that if we sort this portion value, for example, if after sorting it becomes 1, 2, 3, 4, and 5, it becomes easier for us because if you know if a sorted list is given to you or it has a monotonic or biotonic pattern, the most common concept which we use there is binary search, right? And we know the time complexity of binary search is log n. Great. So this completely reduces our time complexity from n cross n to n log n, right? Now, let me tell you how we're going to do that. Suppose let's take an example of spell as 1, 2, 3. Okay, this is the spell. Let portion be 4, 5, 6, 8. Okay, and success. Let the success be 10. Okay, this is a success. So what we could do? We could run a for loop for in the spell because we cannot change the order of the spell. So we put a for loop so we can take each value from the spell. And what we could do? We could take this value of the spell. Suppose spell of I. Okay, and we could run the binary search after that. While whatever the code of binary search is, we will use that. I'm just writing the pseudocode here. And what we can do is that after sorting, we will sort these portions also, right? After sorting, the portion becomes okay. It is already sorted. Just assume we will sort it beforehand, okay? So what happens now? We will do the binary search on this. I will write it here 4, 5, 6, and 8, okay? After indexing 0, 1, 2, 3. So if I do the binary search and take out the midpoint for this, what it will be? It will be 3 plus 0 divided by 2. It becomes 1, right? So this will be the midpoint. Okay. So what you're going to do? We'll multiply the spell value, which is, for example, let's take 2. Okay. 2 into 5. Is it greater than 10 or equal to 10? Yes, it is. Right. So what we're going to do? We will take the complete size of this particular list, which is suppose n, and after that, the mid value. Because if we subtract size of the complete this list minus the mid value, suppose it was 4 minus 1 gives me 3, right? So we know that from mid up to 3 values, if I take any of the values after 5, it will be greater than the 10. The product will be greater than the 10, right? So If we are sure about it because we know the array is sorted. So what we're gonna do after that? And we won't be stopping here. What we'll do? We will move the mid or the higher. We have low and high, right? In our binary search. So we will move the right part or the higher part and reduce the search space from the right hand side. So the edge will come here, right? Why? Because if this is the value which solves our problem, basically the product of the spell and this particular portion is greater than or equals to 10, that means any other value after this type will be greater, will give us a better product, right? So we're assuming that there might be a value which could give us the product greater than or equals to 10 if we move in the left hand side, you know, throwing the right search space, or you could say neglecting the right, removing the right searching space. Okay, if it does not happen, suppose let's take an example. I'm taking a random example here. Okay, let the success value be 30 now. Just a random example. And if we got this 5 and the value was 2. Okay, so if we do 2 into 5, it is 10. So from here we know that the value 10 is less than 30. Therefore, the product that or any product from 5 or up to 5 and before 5 will not give us any result which will be greater than or equal to 30. So for that we have to remove the left search space and move ahead. So therefore what we will do, we'll do L equals to mid plus 1 and we'll reduce our search space. So now our search space will become this one, right? So this is how we gonna solve our problem or iterate through our problem, right? This is what is written here. For a given spell, once you find the portion that satisfies the spell into portion product, all the portions to the right of it, or the larger or equals one, will also satisfy the condition. This is for the one which satisfies the condition, then it will become h equals to mid minus 1, right? Reducing the search space from the right hand side. So the problem reduces to finding the first index, valid index using binary search, right? So I hope you understood how we're going to do that. So therefore, so here we are using iteration also for iterating this spell, and after that, binary search on portion. Pretty straightforward intuition. Now, how are we going to simulate this? So what we'll do, we'll sort the portion array in the non-decreasing manner. Very simple thing. Portion dot sort. Just that sort, right? Create an empty list. V equals to empty list. Okay. For each spell in the array, perform the following steps. What are you going to do? For loop I in let me write it properly. For I in range. Okay. This way we will initialize two pointers for the binary search. Left equals to 0 and h equals to the length of the portion minus 1. Okay. And then we will do the binary search. I hope you understood how binary search works and how binary search code is written. So we'll just write the template of the binary search code here. And in that template, we'll just do one thing, spell of I multiplied by portion of mid. Okay. This is greater than or equals to success. We will store the max of answer or the size minus mid value. Okay, let me write it properly. After this, what are you gonna do? It will basically answer equals to max of answer, comma, and size of the portion minus the mid. This way we got all the values of the range. That means that these are the values which are what we could say allowed to be taken, and this will give the product greater than the success. Okay, and we will reduce the search space by h equals to mid minus 1. Okay, else in else case what happened, L equals to mid plus 1. That is the means that the product which we got is less than the success. Okay, pretty simple. And after this binary search, we'll just put this particular answer, or we will append this answer into the v dot append. Okay, it is what written here. After the loop ends, the value of L will point to the first valid index. The number of successful portions for this spell is this, length of portion minus L. L, or we could say mid. Mid will make much more sense. Append this count to the result list. After processing all the spells, return the result list. Okay. You will understand this much more when you will see the code. Now, what we figured out from the problem, we noticed that once the portion were sorted, we didn't need to check each one for every spell. There's a clear point where portion starts forming successful pair, and everything after that will also work. Suppose if you get this portion value multiplied by the spell, and it is greater than the success, that means that everything after this will result in success. So we go back side or reduce our search space and check from here. Okay. Instead of going through all portions, we can quickly find the starting point using binary search. Okay. It's a great example of how sorting combined with iteration and smart searching using binary search simplifies the problem and reduces the time complexity. So I hope you understood the intuition explanation. So let's move to the next slide. Now, since you got the intuition of the problem, let's look into the approach how we're gonna solve it. So step one, sort the portion array. Sort the portions array in ascending order to enable binary search, which relies on the array being sorted. Okay. Now step two will be prepare the result, initialize an empty list tree to store the final result, and get the length of the spells. And length of the spells because the first for loop will go till the length of the spells, right? That was understandable. Now the step three, iterate over each spell. So basically for loop I in range of n. This is the spell's length, right? And store its value in variable val. Basically, val will have the spell of I. We will have the lower value. We will have the higher value of length of portion minus one. Then we will have the answer here. Okay. This is the things we will do before the binary search happens. Okay. These are required for the binary search. This has the spell value. This will store the answer for each spell. Okay. Now, at this step 4, binary search on portion. After writing all of those, what we will do while L is less than equals to H, right? We will calculate the need this way. Now, in Leetcode, we use this formula to calculate the mean because it sometimes in Leetcode, when we have larger values, it goes to an overflow. We use this formula to calculate the mean in Leetcode because sometimes what happens if the value is much more greater or very much high, it results in an overflow. Okay. That is why we use this formula. It nothing. It is from 0 to 4 the size there. And low value is 1. 1 plus high is 4. Suppose 4 minus 1 divided by 2. So 1 plus 3 divided by 2 gives me 2 at the end. Right. So midpoint will be 2. This is how it works. And we will write this. And after that, we will check that if the well multiplied by well is the spell of I. Okay. Multiplied by the portion. I will write the short form portion of mid if it is greater than or equals to the success. S means success. Okay. If yes, in answer variable we will store the answer. Sorry, we will store the max of answer or what n minus mid. Okay, because mid is the index, right, and n is the total length of the portion array. And after that, h equals to mid minus one by searching. So for reducing the search space, or since we know that from here everything is successful, so we'll go and try for the more values in the left hand side. If it might be a case that okay, that value is also gets in or results in success, so we could increase the count. Okay, that is what we do is. Else, if it is false, we just do L equals to mid plus one. That's all. We want the first portion index that satisfies the condition to count all the succeeding ones. Okay, this is the reason why we are doing this. Now at the step 5, we store the result for this step. Now, after this for loop is done, this BS is done, right? After coming out of the BS, what we do? We dot append the answer variable. Okay. Now after this complete is done, we just return the B. This is the step 6. Okay. So I hope you understood the approach explanation. Let's move to the next slide. The code is the exact copy of the approach discussed. Let's understand it line by line. So here we could see this is the list for storing the result. Length of this file, portion is sorted here, right? This is the range for iterating into the spells array, taking the length of the portion each time, making this ready for binary search, lower end and the higher end. We store the value of spell or file in the val variable. We redeclare the answer variable each time to store the final answer for each iteration. Now, this is the complete binary search code. It's just a simple code. We take out the mid value. We just check, we take the portion of mid here. We check the condition. If it is greater, we store it. We do mid minus 1, otherwise mid plus 1. And after this complete binary search is done, we store the answer in the, or we append the answer into the list which we created here. And after this complete iteration is done, we just return the key. Now for this code, the time complexity comes out to be n log n. N log n. Why n? N comes from the iteration from spells array. Okay? N comes from binary search. Correct? You could just visualize this very clearly. For loop takes n time complexity, binary search takes log n time complexity, n is the size of the portion. Therefore, it turns out to be n into log n. Okay? And this complexity is O of n because the list which we created here is same as the size of the, or it becomes the same as the size of the spells array, which is of size n. Okay? So I hope you understood the code explanation. Let's move to the next slide. Now, since we have the understanding of the code, let's look at a drawing of the example. I have brought down the code here for our clear understanding. So let's start. So what I will do, let's start. Okay. So we have this spells array. Let me write x equals to 5, 1, 3. P means portion, which is 1, 2, 3, 4, 5. In this case, the portion is already sorted. Okay. And S means success. Okay. I've just put the short forms here. Now let's start. So the iteration starts from here. We create an empty list V. I will create the V here. Okay. We take the n spells length. Length of spell is 3 here. Portion is already sorted. Now, size takes the length of the portion, which is 5 here. I will write it this way. Okay, just keep that in mind. I am writing it this way. L is 0, H is SZ minus 1. So, L is standing here, and H is standing here. Now, we are taking this portion in the first iteration. Answer is 0. I will write answer here. Okay, now we will do the binary search. We'll take out the mid value. Mid value will be what? Mid. Full stop. Let me write the indexes 0, 1, 2, 3, 4. Okay. So mid will be 0 plus h is 4 minus 0 gives me 2, right? So second index value is 3 here. Okay. So here it will be 3, right? Or I will write it somewhere. Wait. I will write it here. POT. Value, I'm writing the value here. It's 3. Now we will check for the condition. It is written here pot into well. Now well here is 1, right? 5. So pot into well. So if you multiply this 5 into 3 gives me 15, right? So answer was 0, and we can see that success value is 7 and 15 is greater than 7. So in answer we will have size was 5, mid value was this 2, right? 5 minus 2 gives me 3. So you clearly see this particular range. If I multiply 5 with 3, I get 15, 5 with 4, 20, 5 into 5, 25. Correct? So we will take this 3 here and add it here. After that, we will reduce the subspace. Now h will come in mid minus 1. Mid was how much? 2, right? So it will come here, mid minus 1. We'll start again. Now we'll come here again. We will calculate the values again. It is 0 plus 1 minus 0 divided by 2. So this results in 0. Mid value results in 0. Okay. Now what happens after that? Portion of 0. Portion of 0 is 1, right? So I will write here 1 and answer we will check. So 1 wins. Now after that, if you multiply pot with well, it gives me 1 into 5 gives me 5, right? And it is smaller than the success, which is 7. So what we will do? We will do mid plus 1. If you do mid plus 1 for the L, from here, L comes here. Okay. Now again we'll do the calculation. Now for this, what will be the mid value? 1 plus 1 minus 1 divided by 2 gives me 1. Okay, index 1. So after writing index 1, we put this index 1 here, portion of mid of 1, portion of mid of 1 value is 2, right? So this will become 2. And then after that, we multiply this both here, gives me 10, right? 2 into 5 gives me 10. Now 10 is greater than 7. So what we do? We calculate the size again. The size was what? 5. Mid value is 1. It gives me 4, right? So here, first it was 3. Now it comes 4. So maximum is 4. So we store here 4. Okay. And after that, again we come back, or we could do mid minus 1 here. If we do mid minus 1, it becomes out of range because L cross H crosses L, and this condition becomes falsifies. And so we come out, and in V we append the answer 4. Okay. Now similarly for 1 we will do the same. But here if you could see, if you have understood the triad tail here, you might have figured out if you take a 1 and if you multiply 1 with each value is here, then also the value won't be greater than 7, right? So for the output for this complete thing will for this complete 1 will become 0. Okay. Now after that, if we take the 3, okay, the 3 will also go with the same scenario. Let's take a faster example to complete this. Okay. So if we take 3, these things will be done. So L will be here, H will be here again, value will be 3, and answer is 0 right now. Okay. So we calculate mid value. So again, mid value will become, if you could recall, mid value for 0 plus 4 divided by 2 is 2, right? So I will calculate for you again. It's 0 plus 4 minus 0 divided by 2 gives me 2, right? So mid value is 2. So value will be 3. So for this portion, and if you multiply both of them, we get 9. Okay. So therefore, after that, this part is done. So we take the length. Length is 5. 5 minus 2 gives me what? 3. So our answer becomes 3. And mid also becomes mid minus 1. H comes here. So this is the same iteration I'm doing again. Okay. So I'm just doing it in a short manner. Now, now again we go back. Again we check the design is true. Again we take out the mid value. L is 0. H is 1. Yeah. 1 minus 0 divided by 2 gives me 0, right? So mid value becomes 0. So when the mid value becomes 0, proportion of mid gives me how much? 1. So pot becomes 1 now. Now I multiply this 3 into 1 gives me 3, which is clearly less than success value. So what we do? We do mid plus 1. So from here L comes here. Okay. Again, we take out the mid value. Low is 1. High is also 1. 1 minus 1 divided by 2. So we get 1 at the end. Okay. So mid value is 1. It will come to the portion part here. Mid of 1 is what? 2. So it is 2 now. So 2 into 3 gives me 6. 6 is again less than 7, which is true, which is false, right? So this won't happen. This won't happen. We will come here. As soon as we increase the length of, or we reduce the range, or we could say L crosses H, this complete condition becomes false. We come out of the loop or the binary search. We append the answer 3 into our V. We go back. We check the iteration for this file is also completed. So we return the V at the end, whose output matches to our given output. Right? So I hope you understood the diagram. If you have any doubts or confusion about the solution we arrived at and how we arrived at it, I would suggest going back and understanding the intuition, the approach, and the core of the binary search concept if you don't know. After that, do a dry run by yourself on 2 3 examples, and I'm pretty sure you will understand both the solution and the thought process behind it. Now, since we are familiar with the problem and the solution, Let's move to the lead code and code the solution. So let's start by initializing the empty list, taking the length of the spell array or list, the spells or spells. After that, let me portion. Portion will sort the portion. Then for I in range n size equals to the length of the portion, lower end for the binary search and higher end for the binary search. Answer to store the nth value. Well, we have the spell of I. Now we'll start the binary search. This is a standard pattern for binary search. Okay. L plus H minus L divided to if, and we'll try to store it in the port variable. Port equals to portions of milk. Then what we'll do, if port into well, if it is greater than or equals to the success, uh, if port into well, if it is greater than or equals to the success, we will have the maximum of answer, comma, size minus mid, and we will reduce the search space, else we will increment or we reduce the search space from the left hand side. And after coming out of the binary search, we will append the answer and at the end we will return the empty list. Let's try submitting for the sample test cases. So we have successfully submitted our sample test cases. Now finally submit the solution. So we have successfully submitted our solution. Now the code of the problem is available in my GitHub repository. You can find the link in the description. Thank you everyone.